April 14, 1912, the RMS Titanic is steaming through the North Atlantic at 22.5 knots. She's a leviathan, 46,328 tons of steel. The largest moving object ever built by human hands. To the public, she's a floating palace. To the engineers at Harland and Wolff, she's a masterpiece of watertight subdivision. Unsinkable wasn't just a marketing slogan. It was a mathematical belief. But deep inside the molecular structure of her hull, a silent disaster is already waiting. The ship isn't doomed because of the size of the iceberg waiting in the dark. It is doomed because of the chemistry of its rivets and the temperature of the water. When the Titanic hit that ice, it wasn't just a shipwreck. It was a violent collision between 19th century material science and 20th century arrogance. This is not the story of a tragedy you know. This is the engineering breakdown of why the world's most powerful machine failed. There is a lazy myth about the Titanic that you have probably heard 1,000 times. People say the White Star Line cheaped out to save money. They say the ship was built on a budget. That is completely false. In fact, the financial reality is much more interesting and much more damning. Harland and Wolff built the Titanic on a cost-plus contract. This means the White Star Line paid for all materials and labor, plus a guaranteed fixed profit percentage on top. Think about the incentives there. The more money the builder spent, the more profit they made. So, financially, there was zero reason to use cheap iron. The real enemy wasn't money. It was time. Harland and Wolff were building the Titanic and her sister ship, the Olympic, at the exact same time. This put a suffocating strain on the global supply chain. They needed over 3 million rivets to hold these beasts together. And the supply of best grade iron, the industry standard, simply ran dry. This forced the engineers into a fatal compromise. On the straight, middle sections of the ship, they used massive hydraulic machines to install high-grade steel rivets. These machines clamped the steel with immense, uniform pressure, but the hydraulic machines were huge. They physically couldn't fit around the complex, curved geometry of the bow and stern. So, for the front of the ship, the exact spot that would hit the iceberg, they went old school. They used manual riveting gangs, men with hammers, smashing wrought iron rivets into place by hand. This decision effectively armed the bow of the ship with a completely different, weaker fastening system than the middle. But it wasn't just that the rivets were hammered by hand. It was the dirty secret hiding inside the iron itself that turned the hull into a ticking time bomb. We need to talk about the steel. To the naked eye, the hull of the Titanic looked invincible, but under a microscope, it was hiding a fatal chemical flaw. It comes down to a concept called the ductile-to-brittle transition temperature. Think of a piece of plastic. At room temperature, if you hit it, it bends, it absorbs the energy. But if you freeze that same plastic with liquid nitrogen and hit it, it shatters like glass. Steel does the exact same thing. Modern ships use steel treated to stay flexible even in freezing oceans. The Titanic did not have that luxury. Forensic tests on recovered hull plates reveal a transition temperature of 30 degrees Celsius. That means in any water colder than a warm bath, the steel started to lose its flexibility. On the night of April 14th, the Atlantic Ocean was -2 degrees Celsius. The hull wasn't just metal anymore. Thermally speaking, it was a massive, brittle pane of glass. But the brittleness had a chemical culprit, sulfur. The steel was dirty. It had a high sulfur content and a low manganese ratio of just 6.8 to 1. Modern steel requires a ratio of 12 to 1 to be safe. This chemical imbalance meant the steel couldn't stretch when it hit the ice. It could only crack. But even with brittle steel, the ship might have survived. If only the things holding the steel together hadn't failed first. Remember those manual riveting gangs, the men hammering iron into the bow by hand? They were using wrought iron rivets, not steel. Wrought iron is like wood. It has a grain inside it made of slag. Slag is a glass-like impurity that strengthens the iron if it runs the long way. But if that slag turns sideways, it creates a dotted line of weakness. Forensic analysis shows the Titanic's rivets were packed with 9% slag. Standard rivets should only have 2%. These weren't fasteners, they were defects. When the Iceberg scraped the starboard side, it didn't slice the ship open. That is a movie myth. The collision actually bent the plates inward. The brittle steel cracked, but the rivets faced the real test. Under the pressure, the heads of those slag-filled rivets didn't hold. They popped off, bang, bang, bang. It was like a zipper opening up the side of the ship. The seams parted, and the ocean rushed in. The total area of the hole was tiny, just 12 square feet, the size of a refrigerator. But it was spread out over 300 feet of the hull. That long, thin line of damage was enough to kill the ship. But even then, the Titanic had a chance to escape. So why didn't she just turn faster? Everyone blames the rudder. You will read forums saying the Titanic's rudder was too small. That is a myth. The rudder was perfectly standard for a ship of that size. The real problem was the engine design. The Titanic had 3 propellers. The outer 2 were powered by massive reciprocating engines. They could throw the ship into reverse instantly. But the center propeller, it was driven by a steam turbine. And 1912 turbines had one huge weakness. They could only spin forward when the officer shouted stop. Full astern, the engineers cut the steam. The center propeller didn't reverse. It just stopped dead. This was catastrophic for the steering. A rudder works by slicing through moving water. The faster the water flows over it, the better it steers. Usually, the center propeller shoots a jet of water, slipstream, right over the rudder. That slipstream gives the ship its turning power. But with the center prop stopped, the slipstream vanished. The rudder was suddenly trying to turn a 46,000-ton mountain in dead water. It created a 37-second delay. That is the time between turning the wheel and the ship actually changing course. At 22.5 knots, that delay was a death sentence. The ship drifted forward just long enough to kiss the ice. If they had kept the engines going full speed ahead, the rudder might have worked better. They might have missed it, but they tried to stop, and in doing so, they crippled their own ability to turn. The collision is over, the ship is stopped. Now, the final engineering failure begins. The Titanic was designed to float with any 2 compartments flooded. It could arguably survive 4, but the zipper effect had opened 6. Thomas Andrews, the ship's designer, looked at the blueprints. He did the math in his head. He knew instantly that the ship was already dead. Why? Because of the bulkheads. The ship was divided into 16 watertight compartments, but the walls between them didn't go all the way to the roof. They stopped at E-deck. Why stop there? Because extending them higher would have blocked the beautiful first-class staircases. It would have ruined the flow of the luxury experience. So, they traded safety for open space. This created the ice cube tray effect. Visual of ice cube tray filling with water. Imagine filling an ice tray with a hose. You fill the first slot. It overflows. It spills into the second, then the third. As the bow of the Titanic pulled down, the water simply poured over the top of the walls. It was a geometric progression of doom. Water rushed in at 20,000 tons per hour. The pumps could only remove 1,700 tons. It wasn't a battle. It was a massacre. To make matters worse, there was Scotland Road, a massive, wide corridor on E-deck used by the crew. Once the water reached that deck, it used Scotland Road like a superhighway. It channeled thousands of tons of water to the port side of the ship. This created the famous Lister port. The ship wasn't just sinking, it was being pulled underwater by its own design. Gravity always wins. And now, the men in the boiler rooms had a choice to make. While the water rose, a different kind of engineering was happening below decks. The passengers were evacuating. But the 25 engineers of the Titanic's Black Gang were doing the opposite. They went deeper. Chief Engineer Joseph Bell knew that the ship was sinking. He had seen Thomas Andrews' calculations. But he also knew that, if the lights went out, panic would kill more people than the water. So, they stayed at their posts to keep the massive steam dynamo spinning. They fought a losing battle against the laws of physics. As compartments flooded, the salt water threatened to short-circuit the main electrical board. The engineers manually isolated the flooded circuits, one by one. They kept the grid alive. They also had to vent the massive boilers manually. If cold seawater hit a hot, pressurized boiler, it wouldn't just sink. It would explode like a bomb, tearing the ship in half instantly. So they stood in waist-deep freezing water, opening the valves. Because of their sacrifice, the Titanic didn't explode, and the lights stayed on until 2:17 a.m., just 3 minutes before the ship disappeared. None of the engineers survived, but their deaths rewrote the rulebook of maritime history. After the disaster, the world realized that compliance does not equal safety. The Solus Treaty Safety of Life at Sea was born. New ships were required to have double hulls that went all the way up the sides. Bulkheads were raised to the main deck, and steel chemistry was regulated to ensure toughness in the cold. The Titanic was a prototype that failed, so the modern world could succeed. We like to tell ourselves that the Titanic was a tragedy of bad luck. An unlucky iceberg, a dark night, a missing pair of binoculars. But the engineering truth is much colder. The Titanic was doomed before it ever left Belfast. It was doomed by the brittle sulfur in its steel. It was doomed by the slag in its iron rivets. It was doomed by a rudder design that couldn't turn without a propeller. And mostly, it was doomed by the arrogance of men who thought they had conquered nature. They believed they could engineer their way out of risk. They were wrong. The Titanic serves as the ultimate reminder for every engineer, builder, and creator. Respect the physics, because gravity doesn't care about your profit margins. And the ocean always audits your work.